Now, once you realize that all this is just that this classification boundary is just determined by the weight vector, then this is what you're after, right? So any algorithm that you create, you're basically going to be learning a weight vector of some kind. And ideally, what you would like to do is you would like to learn a weight vector that separates the data well, right? So if dot products are positive, that should happen when documents belong to the positive class. And if it's negative, it should happen when documents belong to the negative class, right? So this particular decision boundary and the weight vector that corresponds to it isn't great, right? It's misclassifying a couple of examples. So we can do, so what we can do is we can make it better, right? So we can, through some technique, we can learn a different weight vector, and that's a weight vector that, that would separate everything, right? So it's nice and straightforward. The only problem is, in most practical situations, there's going to be lots and lots of such vectors, right? And why is that? Because most of the data that you're going to be dealing with in text will be linearly separable. And why is it linearly separable? Anyone has a guess? Why is text generally linearly separable? Doesn't matter what you're looking for, what your classes are. Because we have huge amounts of features, right? Think about how many features you have in text. In a lot of corpora, you're going to have more features, more words in the vocabulary than you have the documents in your training data. So your problem is underspecified in a way. You have more variables than constraints on those variables. So your data is more likely going to be separable, right? Sometimes you'll find cases where it's not, but usually it is, right? So, and what that means is there's going to be more than one way to draw this decision boundary between the two classes, right? So that decision boundary separates the classes. This decision boundary also separates the classes, but they're very different, right? So which one should we choose? And one of the really good ideas, one of the really good developments in machine learning, sort of core ideas that ends up propagating in many areas, is this idea of large margin classifiers. And the ideas of large margin classifiers is, well, you don't just look at whether your decision boundary separates the positives from the negatives, you also look at the buffer zone around the decision boundary, right? So think about the positives and the enemies hate each other, and you have to put a border between them. So ideally, you don't want to put the kind of border that makes every positive and every negative as far away from each other as possible, right? So in this case, you have a buffer zone, and that's just a zone where there is no examples of any kind, no positives, no negatives, sort of the no man's land, the boundary between the Koreas, if you want to think of it that way, right? So in this case, it's fairly small, and you can come up with others for which the boundary would be larger. Now, why is it a good idea? Why are we doing this? We're doing this because this is our training data. This is what our classifier sees now. That's what it knows what's positive and what's negative. And the data that comes tomorrow isn't going to be identical to what you have today. It's not going to be your training data. You're going to get new data points. Right? And what you assume is that they will, in general, follow what you saw in the training data, but they could be different, right? So you'll have positives in different places, negatives in different places. And the basic idea is that if you created a boundary with a large margin, with a large buffer zone between the decision boundary, the red line, and sort of the nearest training examples, then you're probably going to do better on the new data when the new data comes out tomorrow. So, and I guess, so you compare in this case, I'm misclassifying a bunch of examples, right? I'm misclassifying this negative, a couple of positives, actually more than this positive as well, right? So in this case, I'm only misclassifying these two positives, and all the negatives are correct, everything else is correct, right? So in general, this idea of having a buffer is a good and productive idea, right? And what this generally means is that your decision boundary, it's still a dot product. You're still looking at whether the dot product between the document and the weight vector is positive or negative, but what you would like to ensure is that all the positives are big numbers, bigger than 0, right? Some theta that is positive, and for negatives, they're smaller than minus theta, right? So you're separating the positives and negatives not by a thin red line, but by a buffer zone, and you want that buffer zone to be as big as possible. So there's a bunch of different algorithms that implement this idea. The most famous example is probably support vector machines, so we're going to look at that today. It's in general, for linear classifiers, it's going to give you a best-of-class classification accuracy. So if you're looking for an accurate predictor, SVM is your friend. It can be slow to train. So if you're trying to do on a massive data set, SVMs are going to be slow, and you will easily bump into data sets where it's just impossible to use a support vector machine. So if you do use an SVM, don't try to implement it yourself. Use SVM Lite. Right? That's basically probably it's been around a while. It's old. There are some things that claim to be better than it. It's probably one of the better implementations out there. Do look at the license, though. It's not completely open source. Okay, so that's if you want accuracy. Now, if you're working with really big data sets, there are other algorithms, and the example that we're going to look at today is called passive-aggressive. So that's an algorithm that's really fast to train. It's streaming and online, which means you can basically work with it in a streaming manner. You don't have to see all the examples at once. You can update the boundary as the examples come in one by one. It's generally pretty good. It implements the same large margin idea, but the accuracy can and will be lower than a support vector machine, and we'll talk about why. Now, so whatever you do in general, there are some basic rules. When you're working with text, you generally want to stick with linear versions, right? So you're assuming that the data is linearly separable. You can sometimes get better accuracy if you use nonlinear classifiers, but on text they don't tend to generalize terribly well. So the data that comes tomorrow, your nonlinear classifier is really going to mess up on it. So just assume that it's linear and everything's going to do well. Feature selection, dimensionality reduction, topic models, LSI is a waste of time if you're doing classification. So don't even bother with that. But do use basic things, right? TF-IDF weighting really helps. Normalizing documents to unit length really helps. Not always, of course, you want to experiment, but more often than not, it gives you a big